Okay, so last time obviously we finished up chapter three, where we were talking about obviously drawing Lewis structures, the idea of formal charge, the idea of also some exceptions to the octet rule. So unlike sort of perhaps the previous classes you've taken where maybe you draw some Lewis structures, and again where they sort of beat into your head to always do eight, which you should try to always do sort of eight for the octet rule when you're sort of drawing Lewis structures. But there is a lot of sort of exceptions to the octet rule, which is sort of what we finished up upon yesterday. And there's three really sort of major exceptions to the octet rule. One is an incomplete octet, as we talked about, which basically means that we have less than sort of eight electrons around it. That one does pop up a little bit, not a lot, but it does pop up a little bit. And again, usually that is, I would say, in most cases, some type of boron containing compound. Again, boron is perfectly fine with basically just six electrons around it. So that incomplete octet, it's okay. Um, Another sort of common exception is what is referred to as an odd number of electrons. And that's basically where, as the name sort of implied and we talked about, you sort of end up with really an unpaired electron. So we normally, when we sort of apply our electrons to our structure, we apply them in pairs. And you would do that as well in that situation. The only difference is at the end, you would be left with just one electron rather than a pair of electrons. Again, that sometimes is referred to as sort of creating a free radical. It has that sort of one non I'm sorry, one unpaired electron, and it makes it very, very reactive. Again, because it has that one unpaired electron, trying to sort of fix that situation. So that one, to be honest with you, we don't come across a lot. You will see it maybe occasionally, but not very often. So out of the sort of the three sort of exceptions, the one that we talked about at the end there, spent a little bit more time on, which was the expanded octet, is the one that we do commonly sort of come across a lot. And we definitely will come across it here in this chapter. And we start talking about geometry here of sort of these Lewis structures. And that expanded octet is when somebody can basically go above eight electrons. And as we talked about, there's really sort of a location on the periodic table where that occurs. And it's right there. Most people would sort of look at it in terms of sulfur on the periodic table. And basically, sulfur kind of to the right, to the left, and pretty much down. Again, mostly in the non-metal region. Obviously, we're talking about covalent bonding here. Obviously, we have the sort of staircase kind of coming across as well. But sort of in that region where sulfur is on the periodic table has the ability really to do the expanded octet. The reason for that, as we spoke about yesterday, is it's basically period number three on the periodic table, and period number three corresponds to a n value of three, which means it's basically on the third energy level or a principal quantum number of three. And because of that, L values would be 0, 1, and 2, which means S orbitals are available, P orbitals are available. And most important, sort of for that expanded octet, is the availability of those d orbitals. So, again, even though they may not be using those d orbitals up front out of the box, as they start bonding, they do have them available to them to use to sort of, if you want to think about it, kind of stash all the extra electrons. So we do see that sort of expanded octet happening at that sort of situation on the periodic table where those guys are located. And again, down also obviously has d orbitals available to them to do that. That's also why we talked about, also just to clarify and make sure that none of these guys sort of above it on the periodic table, which is in period number two, has an n value of 2, which means L is 0 or 1, has S and P orbitals only. They do not have d orbitals, so these guys go above 8. So again, that's a really crucial sort of distinction. Sometimes people get into the expanded octet and sort of think, well, I could just do that for everybody that I see. And you can't. Again, it's got to be sort of that location down for them to have that ability to do that. What we will see is sort of what we saw yesterday. We could get upwards of really 5 or 6 sort of bonds to the central atom, which basically means we could get upwards of 10 or 12 electrons sort of hanging out around that central atom in that sort of expanded octet. Does come in handy sometimes, as we talked about at the very end there. For example, if we go through sort of our process of drawing something like sulfate, where we single bond sulfate all the way around, um, we can then sort of reduce down the formal charge by applying some of this expanded octet and making a few more bonds to sulfur. And as we saw last time, we were able to really sort of bring down the formal charge in something like sulfate from, especially on the sulfur, from a +2 to a 0 sort of formal charge, again, giving us probably a better structure to sort of draw. So there's some benefits. There are some things that can go above 8 in that expanded octet. I would also, though, caution you not to sort of go crazy with the expanded octet. You should not just try to draw as many bonds as you want to the central atom. Again, I would still follow, obviously, the same rules we talked about in terms of drawing Lewis structures. And again, just applying the expanded octet where you can at that point, not necessarily, making like 6 or 7 bonds to the central guy just out of the bat. Any questions on any of that stuff we sort of talked about last time? So we're then going to jump into chapter 4. And as I mentioned last time, we pretty much finished chapter 3, except for nomenclature, which we will come back to. But we're going to kind of continuation talking here about bonding. In this chapter here, we're going to talk obviously about geometry. We'll also talk about hybridization, which might be new for a lot of you. And we'll also talk about molecular polarity here in this chapter as well. And again, we talked a little bit about molecular polarity in the last chapter and bond polarity for sure. But here we will be looking at in this chapter sort of the entire molecule as a whole, whether or not it's sort of polar or non-polar. But we're going to start with geometry. So let us do that. So let's see here. Oops, come here. There we go. So when we talk about geometry, we're going to talk about really 2 types of sort of geometries as we kind of go through this chapter. We're going to talk about sort of what is referred to as electron pair geometry and the molecular geometry. But the molecular geometry basically refers to sort of the 3-dimensional arrangement of the atoms in sort of space. We can sort of predict it based off of sort of Lewis structures in a sense. We can base it basically on how many electrons we have around the central atom and really how many bonds. So it's really about the central atom always when we do geometry. So that's a really important thing to sort of keep in mind. It's always the guy in the center atom is always the important guy when we do geometries. And as it says there on the bottom, it's really about that center atom and how many electron pairs there are around it, and also how many bonds there are sort of around it. It really sort of dictates to sort of the geometry that we see associated with a particular compound. Now, the basis of this approach is really the idea that when we do make bonds, as we've been talking about, it really involves electrons, right? And when we make electrons, especially in a situation in covalent bonding, where we're sharing electrons, obviously electrons are negatively charged, which means we are going to have situations, obviously in a bonding situation that's occurring, that we're going to have electrons near electrons. And that basically means that we have negative guys near negative guys. And as we know, things that have the same sort of charge doesn't really want to be near each other, right? So they sort of repel one another. So it creates sort of an interesting situation that occurs when you think about bonding. You're using these electrons to sort of sharing these electrons between atoms, but we're sharing things near each other that really don't want to be near each other because they're negatively charged. The problem is they can't really escape. So much like a lot of things sort of in chemistry and stuff like that, no matter what you do, you're always going to get sort of similar charge properties or particles near each other, right? You can get sort of positive guys near positive guys, negative guys near negative guys. For example, in ionic bonding, when all the ions come together, no matter what you do, there's going to be areas where you're going to sort of get the common sort of charge near one another. And what essentially happens in pretty much all these cases is, well, they try to find the best suitable way to manage that. So the best way that they could kind of be near each other with not being so near each other that they're going to try to run apart as far away as they can and break apart. And that's the same thing that happens when we talk about bonding and these negatively charged electrons. As they sort of come together to share, in certain cases, depending on how many electrons are there, actually what type of electrons are there, whether they're bonding electrons, non-bonding electrons, that makes a big difference in really how sort of happy they are being next to other electrons. There are certain situations, as we'll talk about here, where if you get a certain type of electron near another type of electron, it's going to do its very best to try to get as far away as it can, that's possible in a bonding situation. So if you just logically sort of think about that, if you got these two guys sort of, or whatever, electrons holding this thing together, and they really don't want to be there, and they try to get, sort of away from each other, what that's going to do is sort of affect the overall shape of a particular molecule. And that's essentially why we get these different sort of shapes that we associate with certain compounds based on the number of bonds, the number of electron pairs that are present. And we get these sort of differences in geometries that we see. The basis for sort of this idea is one that's referred to as VSEPR, which is valence shell electron pair repulsion model, probably why they abbreviated it there. And it basically accounts for these sort of geometrical arrangements that we see around the central atom. So again, that center atom is really the importance, as we talked about a little bit when we were drawing some Lewis structures. And a lot of sort of compounds that you deal with in this class, for example, there's really just one center atom. It is possible you could have multiple central atoms, as we, I think, maybe drew one the other day. For example, when we did nitric acid, when we drew that one, the HNO3, there actually was two central atoms. So you could apply geometry to every central atom you have. You could do them sort of separate from each other. But it's always the central atom is always the one that you want to look at. It's always the one where you want to kind of start in terms of geometry. Now, when we do talk about geometry, as I mentioned just a second ago, there's really kind of two types of geometry, or two names of geometry that we sort of talk about. And those are, one really describes sort of the three-dimensional arrangement of basically how the electrons are around the central atom. So when we look at the electrons, it's basically how those electrons are around the central atom. And that's what is sometimes referred to as the electron pair arrangement or geometry. So the electron pair arrangement simply describes, how many electron pairs there are around a central atom, sort of the arrangement of those electron pairs, be it bonding pairs, non-bonding pairs, it really doesn't matter. The other geometry that we talk about is one that's referred to as the molecular geometry. And that also is sometimes referred to as the shape. And when we talk about sort of molecular geometry, a result of what I was just talking about, sort of the electrons need to sort of separate out from each other as far as possible. What that does in certain cases is it really does sort of play with the overall shape of the molecule. So you got to remember that pretty much everything is locked into place through bonds. So, if one thing moves, other things move around as well. And, as these electrons try to escape each other, we really do start to see some different geometries or shapes occur. When we look at sort of geometry, we really can divide the molecules into two categories. One is where we have a central atom that has no lone pairs. So this is a central atom with no basically bonding on no dots on it, basically. Remember, lone pairs are non-bonding electrons. And that basically means we have no dots on our Lewis structure, right? And central atoms that do have lone pairs, which means when you draw the Lewis structure, you have dots on the central atom, right? Remember that the dots represent obviously the non-bonding electron, and non-bonding electrons and lone pairs are basically the same thing. Now, there's two important sort of considerations, but the first one really is the most important, and especially when you're doing geometry, it's a really important rule to remember, and that is if you have a double bond or a triple bond when you draw your Lewis structure, we treat all double bonds and triple bonds as if they were single bonds, and also single electron pairs. So that's a really important thing to keep in mind as we go through geometry is when we come across, and again, this is strictly for really geometry and doing geometry, that when you come across a double bond or a triple bond, either one, part of what you do typically when you sort of apply geometry is you count up how many electron pairs there are and how many bonds. Those are two really important things. Basically, when you do a double bond or triple bond, it counts as only one electron pair, and it also counts as only one bond. So that's two really important things to keep in mind when we do geometry. And again, only specifically for geometry. So obviously if you had just a standalone question and you had like a double bond in there and asked you how many bonds there would be, you would say there's two bonds. But if you're doing sort of geometry and you're looking at that double bond, you think of it as one electron pair and one bond. The idea for that is even though it's sort of double bonded or triple bonded, those electrons are basically acting sort of as one unit. And because they're acting as one unit in terms of geometry, we treat them basically as they were basically single bonds and one electron pair. The other sort of consideration that you can do is what it says on the bottom. And again, we talked about resonance structures, and resonance structures, again, is a situation where if you have sort of options as to, where you can draw the double bond like we did with a carbonate and so forth. You can basically apply VSEPR here to any resonance structure. And for the most part, if you draw pretty much a legitimate resonance structure, you can apply this geometry to any of them, and you pretty much will hit the exact same geometry. So, for example, even if you think about what we did with sulfate, and we did single bonds versus double bonds, you actually will end up, if you sort of pretty much 99% of the time, if you basically draw a correct resonance structure, maybe double bonds here, double bonds there, and so forth. In terms of geometry, it really will not usually make a difference. You basically could apply this sort of geometry approach to it, and you will end up with the same overall geometry, regardless of sort of what your resonance structure sort of looks like. All right, so let us start then with really, the most simple and easiest geometries basically to basically figure out, and that is basically diatomic molecules. So diatomic molecules are pretty much when we have basically two atoms bonded together and nothing else. So two atoms bonded together, we basically have one bond that's present, and those create really the simplest sort of geometry that you could have. So when we talk about diatomic molecules, it's basically two guys together with one bond. I mean, that's just pretty much as simple as you could get. The geometry of this, you really don't even have to think about it. It's going to be linear 100% of the time. So the geometry here will be linear. Again, if you think about what's that saying, the shortest distance between 2 points is a straight line. So if you just have two things, they're going to be connected via a straight line. And the geometry will always be linear. Now, sometimes people think, well, what about, does it matter a couple of situations where we have diatomic molecules? So, for example, if you had H2, it's going to be linear, the geometry. If you had F2, it's going to be linear. If you had HF, doesn't need to be two of the same, going to be linear because there's only one bond. You know, if you had HCl, also going to be linear. In addition, sometimes people, well, what happens if you had something, say, like oxygen here, double bond? Doesn't matter. It's going to be linear. If you had something like we saw nitrogen, which involves a triple bond, doesn't matter. It's going to be linear. So they really are the simplest. It can be two of the same elements. It can be two different ones. You could have a single bond, double bond, or triple bond. But if you only have a grand total of basically two atoms involved, diatomic molecule, geometry will always be linear. The idea here is, to be honest with you, there's really not a central atom, obviously, in this situation. So with only two atoms present, clearly there is no, somebody in the middle or something like that. So there's no real true sort of central atom that's present. So we really just talk about the geometry of it being linear. And in most cases, we just talk about it as sort of the molecular geometry. As again, there's really no central atom to talk about electron pair geometry. Some people just call it, kind of linear for both, but really it's the molecular geometry here we're talking about, again, because there's really no central atom. In order for sort of electron pair geometry and so forth, we typically do need sort of a central atom. And that usually occurs when we get three or more atoms present in a particular compound. So two atoms present, diatomic molecules, very simple. Geometry is always going to be linear, basically a straight line between the two connecting. And obviously, when we get to things that have more than two around it, which we're going to talk about right now, obviously some things are a little bit different. So let us start talking about geometries here that again involve three or more atoms. And the first one we're going to come across is basically a central atom. That's what A stands for here, and B stands for atoms on the outside there. So a central atom with two things attached. And we get a couple of things here. First off, when we look at this, remember that we are going to be looking at really two types of names. And again, one name is what is referred to as the electron pair geometry, and one is the molecular geometry, or the shape. Now, whenever you do geometry, and sometimes people again get a little confused about, where you should look. You should always look at the central atom. So no other atom is important in terms of geometry other than the guy dead there in the center. And really, there's two things that you really want to look at when you are sort of doing geometry that I find is really important. The first thing you want to look at is how many electron pairs are there. And in this case, electron pairs could be bonding electrons, non-bonding electrons, which means when you look at your Lewis structure, they could be dots, they could be lines. So here we have one electron pair and two electron pairs. So when we talk about electron pairs, two electron pairs. The other important thing that you want to talk about is how many bonds there are. So there's one bond there, two bonds there, and two bonds there. So first off, when we talk about something that has two electron pairs around the central atom, that gives us a electron pair geometry of linear. Basically what that means is these electrons are going to try to get as far away from each other as possible. And they could do that because they're basically only two things bonded. Electron pair can kind of go this way. I'm going to get away from you. This electron pair on the right is going to go, I'm going to go as far away as they can. And what they end up doing is giving a bond angle in that case of 180 degrees in terms of the bond angle. And that's based on the electron pair geometry name. The result of that is as these bonding electrons move, because they are bonding electrons, they're going to take the chlorine for the ride, right? So as those electrons kind of move to either side, they actually do take the chlorines with them as they're moving. The result of that is for the molecular geometry here, we actually do get a geometry that is also known as linear, basically, again, 180 degrees from each other. So basically what we have here is basically two bonding electron pairs that decide I want to get away from you as far as I can. Because there's only two atoms, they then can kind of go basically side to side of each other, as far away from each other, 180 degrees, basically away from one another. So when you approach a Lewis structure that you draw, that's sort of how you want to approach it. You want to think about it in terms of how many electron pairs there are around the central atom and how many bonds. So 2 electron pairs and 2 bonds gives you an electron pair geometry name of linear, and also a molecular geometry name of linear with a bond angle of 180 degrees difference, basically a straight line, as you can kind of see there. Let's take a look at another example here of another sort of structure. Here we're going to have a central atom that has basically 3 outside atoms attached to it. Again, here, if we look at our central atom, which is the important guy, we see that we have 3 electron pairs. Again, right here, 1, 2, and 3. And we also have 1 bond, 2 bonds, and 3 bonds, and 3 bonds that are basically occurring. Again, the electron pairs around the central atom is what determines our electron pair geometry. And our electron pair geometry with 3 electron pairs is one that is known as trigonal planar. Some people will call it triangular. And basically, with 3 electron pairs, what ends up happening is these guys again try to get away from each other as far as possible. The difference, though, is we now have 1, 2, and 3 bonded atoms that are there. So because of that third bond, they can't go 180 degrees away from each other, because as they move, you got that third guy kind of moving with them, and it's got to keep some space between these guys and these guys that are bonded there, all those atoms, to try to get everybody to sort of come out together in a sort of reasonable way that they're going to be happy. So what ends up happening is they do spread out in this bond angle of 120 degrees, and 120 degrees basically makes like a equilateral triangle, which is why it's sometimes referred to as triangular if you just kind of draw the triangle right there in sort of 3-dimensional space. And the molecular geometry name in this particular case is also going to be trigonal planar. So we get this bond angle. Again, these bonding guys, just like what we had in linear, are going to try to get away from each other, but because of the presence of this third sort of bond, they can't get 180 degrees away from each other. The best that they can sort of do in this situation is get about 120 degrees away from each other, again creating this sort of equilateral triangle that you could kind of see there. And again, this is what is referred to as trigonal planar. Any questions on that there? That's a good question. And the question was, is the name of the electron pair geometry and molecular geometry always going to be the same? And the answer is actually no, they're not always going to be the same. They do happen to be the same right now. And we'll talk about sort of why they're the same in just a second, and what will make them different in terms of their names as well here coming up. But the quick answer to your question is they will not always be the same, but in certain situations, as we see here, at least with these first 2, they definitely are the same. And again, we'll talk about sort of why that is in just a second. Other questions on that? Okay, so then let us take a look at the next sort of example. Next example that we have is a central atom where we have basically 4 other atoms attached. And in this situation, it does create some different sort of geometries that we look at, again, we want to make sure we always go to that central atom. And that central atom right here has 4 electron pairs around it. So 1, 2, 3, and 4 electron pairs. And it also has 4 bonds. So this has 4 electron pairs and 4 bonds. Again, when we talk about electron pair geometry, it is all about how many electron pairs there are. So there's 4 electron pairs. Something with 4 electron pairs in terms of electron pair geometry gives us something which is referred to as tetrahedral, tetrahedron, some people call it years ago. Most people call it tetrahedral now. But tetrahedral is the arrangement when we do have those 4 electron pairs around it. And we also have 4 bonds. So what ends up happening in this case is, again, all these electron pairs want to really sort of get as far away from each other as they can. But the difference is here, we've now instituted one atom that's bonded, 2, 3, and 4. So remember, as these guys try to get away from each other, as these guys get away from each other, and so forth all the way around, as sort of one of those bonded atoms move, the other one moves as well, until they basically rest upon this sort of geometry here, which is tetrahedral, which has a bond angle of 109.5. It's sort of a triangle on the face and almost like a pyramid type shape there on the bottom, and it creates this 109.5. And the molecular geometry here is also going to be referred to as tetrahedral. So both the electron pair geometry and the molecular geometry here are both going to be tetrahedral in this case. Again, because now we've added one more bonded atom to the mix, it limits how far away everybody can kind of escape to each other. Remember, again, everybody is pretty much bonded together, which means as one moves, the other one has to move sort of appropriate to it, and they can't get away. Remember when we talked about sort of at the very beginning there, 2 electron pairs and 2 bonds with only 2 atoms involved, there's nobody in the way. They could just go 180 degrees apart from each other. Again, when we do kind of 3 involved, they can only get about 120 degrees apart. And now when we get to sort of 4 involved, they can only get to this sort of 109.5 sort of difference apart from each other. And again, it's all about sort of getting to a situation where they're sort of okay with, sort of what's happening in terms of their spacing and something that they could kind of live with. And it's really, when we talk about this sort of moving and stuff like this, it's really when they do that and they're kind of moving around, they're really sort of minimizing their overall energy. So they're trying to find these good sort of arrangements overall in terms of geometry where, they're not getting a lot of repulsion happening, not getting a lot of that sort of situation happening, but there is some of it happening, obviously, but a sort of livable situation that they can kind of do that. So again, here we do see, as the question was a second ago, both of these names are going to be the same. And we'll talk here in just a second when we'll get some differences here and why these are the same. Now what we're going to talk about is a situation where we do have a central atom that actually has 5 bonded guys to it. And in this situation, we have our central atom. And in this case, if we count up how many electron pairs there are, 1, 2, 3, 4, and 5 electron pairs. 5 electron pairs definitely puts us over the octet rule. So 5 electron pairs. Also has 1, 2, 3, 4, 5 bonds happening. Now, up to this point, you probably have seen perhaps some of those geometries that we've been talking about, but we're now into our expanded octet here. So we're into our exceptions to the octet rule, and there are geometries that go with those sort of expanded octets that we commonly come across. So when we deal with 5 electron pairs, the electron pair geometry has a name of what is known as triangular bipyramidal. And in a triangle bipyramidal, there's actually 2 different bond angles that are occurring, 120 degrees and a 90 degree. So over here, I sort of have the right angle here. We have sort of that right angle happening here, that 90 degree sort of bond angle that's occurring. And we also get basically a 120 degree, like what we get with our trigonal planar sort of happening through here, that sort of triangle sort of situation that's occurring in that area right there. So you got this on a triangle sort of occurring here that's 120 degrees. And it gives us some positions. These are what are sometimes referred to, as you can see here, these are axial chlorines, so kind of like on the axis going straight through. And these are equatorial, like on the equator sort of chlorines coming across the middle like the equator and stuff like that. So when we have 5 electron pairs, it does correspond to triangular bipyramidal. It results in actually a couple of different bond angles sort of occurring from that central atom. In addition, something with 5 electron pairs and 5 bonds, in terms of the molecular geometry, also going to have a name known as triangular bipyramidal. So again here, both of these names are going to be the same. Both the electron pair geometry and the molecular geometry are going to be the same. Here we got our expanded octet happening here. Now, in addition, we talked about, when we talked about sort of the expanded octet, we could have 5 electron pairs around the central atom, which gives us 10 electrons. We also can go upwards of 12 in most situations, and that gives us another geometry in the expanded octet. So taking a look at what we talked about the other day, which was SF6, SF6 is a central atom that has 6 electron pairs hanging out there. So 1, 2, 3, 4, 5, and 6 electron pairs. So we have 6 electron pairs, which is 12 electrons. Also has 6 bonds if you go all the way across. Right, so 1, 2, 3, 4, 5, and 6. And 6 electron pairs obviously gives us 12 electrons, which again puts us in that expanded octet, kind of exception to the octet rule. Something with 6 electron pairs is an electron pair geometry, what is known as octahedral. And with 6 bonds, what it ends up giving us is these sort of right angles, basically, they're happening with 90 degrees. And we end up with a molecular geometry of octahedral as well. So again, here we end up with both of these names being the same. Now, to answer the question that was asked earlier, both of these names are exactly the same. The electron pair geometry name and the molecular geometry name is the same. And in fact, if we go back and sort of take a peek at all of them, everyone that we talked about up until this point, both of the names, the electron pair geometry name and the molecular geometry name, are exactly the same. So the question is, what do these guys all share in common to allow those names basically to be the same? And what they all share in common is, when we look at the central atom, there's absolutely no non-bonding electrons. So the only type of electrons we had here were bonding electrons between the Be and the Cl. By the way, this guy was an incomplete octet, right? This guy. When we look at this central atom here, absolutely no non-bonding electrons, no dots around the central atom. They're all bonding electrons. Same thing when we looked at this guy. When we look around the central atom, no dots around the central atom. All the electrons there were bonding electrons. Same thing here with our expanded octet. absolutely no dots around the central atom, all bonding electrons. And finally here, when we got to here, again, all bonding electrons around the central atom, no non-bonding electrons involved. So when we are dealing with a situation where if you draw your Lewis structure and pretty much what you have drawn around the central atom is all bonding electrons. So if we have all bonding electrons around the central atom, which basically means no dots when you draw your Lewis structure. Both the electron pair geometry name and the molecular geometry name are the same. And the reason that they're the same is because they're all bonding electrons. That pretty much means that every electron pair at the other end has an atom that's attached, right? So there's an atom that's basically attached. So as those electron pairs move, so does the bonded atoms move, and they move the same. And that results in both how the electron pairs orient themselves and how the overall sort of atoms and the bonds basically orient themselves. They're going to orient themselves in basically the same three-dimensional space. And that's because, again, there's pretty much everybody there bonded, and they can all move basically, they all kind of move together in that sense. So they're always going to be the same name. Pretty much when you draw your Lewis structure and you do not see dots, both of those names are going to be the exact same name. Any questions on that? So then the question becomes perhaps, when are they not going to be the same? So they're not going to be the same when we start introducing different types of electrons around the central atom. And there's really only two types of electrons around the central atom, right? There's basically the bonding electrons or the non-bonding electrons around any atom, basically. There's either bonding electrons or non-bonding electrons. But because there's only basically two types of electrons that can be present, it actually creates three different types of interactions that can occur when electrons get near each other. So again, remember the whole idea of sort of this bonding and geometry is that we have electrons near electrons, and again, they're all negatively charged, which basically means they don't want to be near each other. So when we get these two different types of electrons, and again, just a reminder that, basically what we're talking about is, you could draw your Lewis structure here, and these are bonding electrons, but we could have some non-bonding electrons involved as well. And the presence of basically dots and lines in your Lewis structures, which represent basically our bonding electrons and our non-bonding electrons, actually create three different sort of interactions that occur. You could have bonding electrons near bonding electrons, which is what we've been talking about in the last several examples, basically lines near lines. And that's pretty okay. They're going to try to kind of spread out as best as they can. The next sort of worst thing in terms of repulsiveness is when you get kind of non-bonding electrons near bonding electrons. So these are like dots near lines, not so good. Lines near lines, okay. Dots near lines, not so happy to be near each other. They're going to try to get away from each other a little bit further. The worst situation that you could kind of have happening is if you get some dots near dots and or non-bonding electrons near non-bonding electrons. That's sort of the worst situation. They definitely don't want to be near each other, and they're going to basically spread out. So what does this really affect? Well, what it affects is we have basically two names. We have the electron pair geometry name, and we have the molecular geometry name. In terms of the electron pair geometry name, it has no effect. And what I mean by that is it doesn't really matter what type of electrons you have. You could have bonding electrons, you can have non-bonding electrons, but the name of the electron pair geometry name stays the same. So if you have 3 electron pairs, that's still trigonal planar. If you had 4 electron pairs, it's still tetrahedral. Doesn't matter if the 4 electron pairs are like 2 bonding and 2 non-bonding pairs. The total number of electron pairs basically still determines the electron pair geometry. It has no effect. The thing that it does have an effect on is this guy, which is the molecular geometry name. The molecular geometry name will start to change once we have these sort of non-bonding electrons involved. And why is that? Well, that is because in a situation, say like what I drew here, we have these bonding electrons near bonding electrons that want to get away from each other. But then we also have these non-bonding and non-bonding guys that want to get away from each other. And what they could do is, because there's actually only 2 bonds here, kind of opens up this space now, right? There's nothing really bonded there. It allows those bonding electrons really to go kind of far away from each other. And it also allows those non-bonding electrons to kind of do the same thing, kind of like, I'm going to also try to get away from each other. And they're able to do that because hanging off of these ends are not another atom, so that they could kind of get away from each other a little bit more. There's a little bit more room for movement. And what it basically affects is sort of the overall shape, basically, of the molecule there. It's able to kind of really start to move a little bit more because it's missing those extra bonds that normally would be there in sort of a 4 electron pair, 4 bond situation. And those atoms are not there. It gives it a little bit more room to move. And we start to be able to see the geometry kind of shift a little from where it's at, or where it normally would be if it was all bonding electrons like we just saw before. So we do start to see these differences occur when the presence of non-bonding electrons are there. And really, because we're not like locked into place, as opposed to, when we would have, 4 guys sort of bonded there. Again, they can only get so far from each other because there's actual atoms involved. By removing a couple of those atoms, kind of out of the way, it allows those guys a little bit more room to sort of flex and move the overall shape of the molecule. And that's why the actual molecule or molecular geometry name is the one that changes in that particular case. Okay, so let's take a look at some examples of this where we do have some of those interactions basically occurring. So the first one we'll talk about is basically a central atom with 2 guys attached, and the E in this case, you don't have to worry about sort of this arrangement, but basically the A is the central atom, B are the guys that are on the outside, E is the number of electron pairs around the central atom. So when we go to our central atom and this sort of guy, this is SO2, we want to look at the central atom, and we basically want to do the same approach as what we did before. We want to count up the total number of electron pairs. So in terms of electron pairs, when you're counting those guys, it doesn't matter if they're single bonds or dots or lines, whatever it may be. This is 1 electron pair. That is 2 electron pairs. And remember that the double bond only counts as 1 electron pair. So even though it's a double bond, that would be a grand total of 3 electron pairs in this case. So this has 3 electron pairs. Now, in terms of bonds, we have 1 bond here. Again, when we're dealing with a double bond or a triple bond, it only counts as 1. And that double bond there would also only count as effectively 1 bond, which means we end up with a grand total of 2 bonds in this particular case. Now, when we think about the electron pair geometry, again, as I mentioned, that name does not change. So ultimately, we have 1, 2, 3 electron pairs. So if you think back to what we were just talking about earlier, something with 3 electron pairs is what is known as trigonal planar in this case. Now, because in a typical trigonal planar situation, like we talked about before, a straight trigonal planar, that is where we ended up with 3 electron pairs and 3 bonds. Because there's those 3 atoms involved, they're only able to kind of spread out in sort of a triangle type way for our molecular geometry. In this particular case, we kind of eliminated that 3rd atom, and it's basically our non-bonding electrons. And what that allows it to do is, as you can kind of see here, it allows those bonded atoms to actually move a little bit more and bring those non-bonding electrons sort of coming this way. And because of that, the molecular geometry name actually does change in this case. And the molecular geometry name is one that's referred to as, I personally call it angular. A lot of people do call it angular. Some people call it bent. And it's really bent angular. Sometimes people will call it as well. So I personally think we should go with angular here, and I'll explain it to you in just a bit why I think we should go with angular here. But I will say people still kind of call this bent, and some people call it bent angular as well. And in terms of the bond angle, again, because we are missing that 3rd bonded atom here, and it's just the non-bonding electrons, it does allow this angle that we have, typically in our sort of trigonal planar, right? The bond angle for trigonal planar is 120 degrees. We can actually get a bond angle a little bit less than 120 degrees. Again, because of the non-bonding electron pair that's here, it gives those guys a little bit more movement, and it's able to bend a little bit more than the 120 degrees. And we actually end up with something a little bit less than that sort of 120 degrees. In terms of interaction, in terms of electrons, if you think about the different types of electrons that we have sort of happening here, we have definitely bonding electrons near bonding electrons, right? So bonding electrons near bonding electrons. And we also have non-bonding electrons near bonding electrons. So the best situation, and then starting to get some of that not so good situation happening as we have, again, our non-bonding electrons near our bonding electrons. Again, these guys want to get a little bit further away from each other because of that. And again, we start to see a difference here in our molecular geometry name. Any questions on that there? Yeah, so a double bond's question is about why is the double bond sort of considered one bond and really one electron pair. So both the double bond and the triple bond, they effectively, the way you can kind of think about it is they sort of act as sort of all those electrons and everything within, let's say, a double bond or a triple bond or even a single bond. In the realm of sort of geometry and stuff like that, they sort of move sort of like one effective unit. So, they're just kind of moving around just like they would as a single bond. And the presence of, say, the extra electrons for the double bond or the triple bond really will not have any sort of overall effect because there's more electrons in there than there is, say, in a single bond. And that's because they're really just all being shared. And as they move effectively, basically as one. So in the terms of geometry, we think of double bonds or triple bonds as effectively one electron pair and also one bond. And again, the only difference really, kind of between them, as we sort of talked about, is a single bond obviously would be longer, double bond would be a little bit shorter, and a triple bond would be even more shorter there along the way. And again, they're effectively still working as one. So when we think about it in terms of geometry, it works as one electron pair or one bond. Other questions like that? Okay. So let's take a look at another one here. So the next example we're going to look at is NH3. So this is a central atom that has basically 3 guys attached and 1 lone pair basically there. So if we approach it the same way, if we look at our central atom, which is where we want to look at it, again, we were counting all electron pairs, when we're doing electron pairs, doesn't matter if they're bonding or non-bonding, so dots or lines. So when we look at the electron pairs here, there is 4 electron pairs around the central atom. And when we think about bonds, there is 1 bond, 2 bonds, and 3 bonds basically happening. Again, same idea as what we've been talking about. The electron pair geometry name is always based on the total number of electron pairs around the central atom. And again, you can see 1, 2, 3, 4 gives us our tetrahedral arrangement. As you again can kind of see that tetrahedral thing with our electron pairs. But again, we have some bonding electrons near bonding electrons. We have some non-bonding electrons near bonding electrons. Again, in a normal tetrahedral arrangement, we have 4 bonded pairs with another atom sort of up here. And in this case, we don't have that. So that's going to give this overall shape a little bit more flexibility, if you will, and way to sort of move. And we end up with this geometry, which is known as Trigonal Pyramid. So the molecular geometry becomes and you could kind of think about it just like the name. You got this again sort of triangle sort of guy up on top, and on the bottom it makes this pyramidal type shape that basically occurs coming down. So that's Trigonal Pyramid it is. And again, the bond angle is really based off of our tetrahedral, but because of that missing sort of 4th bond, giving it a little bit more flexibility. So it will be a little bit less than the normal tetrahedral arrangement of 109.5 degrees. And as you can see in this particular case, it's actually 107.3 degrees. So a little bit less than that normal tetrahedral arrangement because of that. Now, let's take a moment here and talk about 2 names that sometimes people, I don't want to say confused, but sometimes people hedge their bet because maybe they're not 100% sure of sort of what the answer is. So remember that this name here, which is Trigonal Pyramid, and a name that we saw earlier, which is Trigonal Planar, which again is 3 electron pairs and 3 bonds. These 2 names are different. They do mean different things. So if you are given the molecular geometry name, you should write out the correct name for it. Do not let me choose, and do not hedge your bet by doing what a lot of people will do and go, yes, it is trigonal. And that's all I'm going to write because you will get probably one of those. Or my other favorite one, I'm very confident it is trigonal. I'm not sure. Oh, it's planar. That's definitely planar. Pyramid, I mean, that's pyramid, you know. So, you know, it's very common when people come across one of those geometries, either trigonal planar or trigonal pyramid, that they just write trigonal, and that will not be accepted. So you do need to make sure you write the sort of correct name for it, either trigonal planar or trigonal pyramid. Again, do not let me choose because I will probably choose wrong and probably not give you the points for it. So, you know, make sure you do sort of choose that. And another geometry here that kind of goes with our non-bonding electrons is one that you probably have seen before, perhaps. And this is our central atom where we have 4 electron pairs. In this case, again, 1, 2, 3, and 4. And in this particular case, we have only 1 bond and 2 bonds. So just like what we've been talking about before, our 4 electron pairs is still going to be tetrahedral. because it does have 4 electron pairs. So remember, that name really doesn't change. It's just based on how many electron pairs there are. But now we actually have all the electron interactions happening. We have bonding electrons that are near bonding electrons, so lines near lines. We have non-bonding electrons near bonding electrons, like we were talking about previously, basically dots near lines. And now we have the third and sort of worst interaction that occurs, which is non-bonding electrons near non-bonding electrons, dots near dots. And because of that, those sort of non-bonding electrons and non-bonding electrons, they want to get away as far as possible from one another. And they're actually able to do that because in this situation, unlike a traditional straightforward tetrahedral arrangement, where it's tetrahedral, and we got 4 guys bonded. In this case, we're actually missing 2 of those bonds, and that gives those non-bonding electrons a little bit more sort of room in the overall geometry of this guy, some room to basically kind of move and tweak itself to find a sort of happy arrangement. And what ends up happening is sort of what we see over here. These non-bonding electrons decide we're going to kind of go up and as far away as possible from each other, also far from these guys, and then also create these guys, creating a distance between the bonding electrons and the bonding electrons. Remember that these guys, you know, not as bad in terms of interaction, but definitely these guys want to get away as far as possible. And all that sort of moving around and stuff like that, it creates a molecular geometry, which is known as bent or V-shaped. Because as you can see, it makes kind of like a bent or backwards V, if you will, or upside down sort of V. And because of those lack of those extra sort of atoms there and the ability for it to basically kind of spread out a little bit more, we do get a bond angle that's less than our traditional 109.5 degrees that we see with tetrahedral. And in this particular case for water, you can see it is a 104.5, which as you can see from the one we looked at before, with the lack of that extra atom not being there, we're able to give a little bit more room for everybody to move around. So we actually go from like a 107 bond angle to like a 104 sort of bond angle because of the lack of those extra sort of atoms that are present in this particular case. So this is what I was talking about a little bit earlier. So if you remember, we just talked about the SO2, where we had the angular, and again, some people do talk about it in terms of it being bent. I personally think for our class, we will go with angular for the previous one versus bent, and we will say bent or V-shaped for this geometry, which is typically what it is used for. And the real reason for that is, you know, if you sort of call this guy bent just straight out, and again, I'll be honest with you, people do, but if you do call this guy bent, most of the time people are thinking about the bond angle that we were just talking about, which is, you know, less than like 109.5. When in reality, in this guy's situation, we're really talking about a bond angle less than 120. So there is a difference in terms of sort of the bond angle between sort of our three electron pairs and 2 bonds versus what we see here with water, which is our 4 electron pairs and 2 bonds. There is an actual difference sort of in the bond angle. So for us, like SO2, you should go with angular, and you should reserve bent, or you could do V-shaped here for this more bond angle that's more less than 109.5 and kind of closer to the water sort of shape. Any questions on that there? So these, again, a few of these here should be some geometries that perhaps you've seen before, but now we do remember that we did get into sort of the expanded octet, right? So we got to those sort of more than 8 electrons around it. And in addition to sort of the bonding and bonding sort of situation, equal electron pairs and bonds, there's also situations where we get non-bonding electrons in that expanded octet. And that does give us some more geometries that occur. And let's talk about some of those right now. So let's take a look at, first off, this guy here. In this case, we want to focus in on our central atom like normal. So we want to kind of do the same thing. So on our central atom, we have 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs, and 5 electron pairs. So obviously 5 electron pairs puts us at the expanded octet. And in terms of bonds, though, we only have 1 and 2 bonds in this case. So just like we've been doing with the others, here with our 5 electron pairs, in terms of the electron pair geometry name, it really doesn't change. So our electron pair geometry name, something with 5 electron pairs, was our triangular bipyramidal. But now we got a couple of situations. We have definitely all the 3 situations occurring. We definitely have non-bonding and non-bonding. We got bonding and bonding and non-bonding and bonding electrons sort of happening. And in this case, because we are missing 3 actual bonds in a traditional triangular bipyramidal molecular geometry, it gives these guys a lot of room to sort of move around. And what ends up happening is these non-bonding electrons just really don't want to be near each other. They actually start to move out in this sort of triangular sort of pattern. And that allows the bonding guys to basically end up actually 180 degrees apart from each other in a linear geometry. So these guys are able to kind of, then the bonding guys, because those non-bonding guys are going to kind of spread themselves out in this triangle sort of form, are able to sort of spread themselves out into 180 degrees. And that will give us a molecular geometry of linear in this case. So again, here we're starting to see perhaps some same names in terms of geometry. This linear is the linear that's associated again with the expanded octet, not to be confused with the linear that is basically our 2 electron pairs and our 2 bonds. Yeah, so essentially, really, the molecular geometry really is, the question is, I think, was molecular geometry sort of based on how many electron pairs are around the central atom. The molecular geometry is really based on how many electron pairs there are around the central atom and sort of what types of electron pairs. Are they bonding electrons or non-bonding electrons? Again, because when we do get those sort of non-bonding electrons near each other, they really don't want to be near each other, so they are the ones that are going to try to get away as far as possible. And they're able to sort of do that because they're not really bogged down by being bonded to an atom. So when we have a guy that's bonded to an atom, because it's basically those electrons are sharing with the atom it's bonded to, and the other guy kind of locks those electrons into place and only allows it to move so much. And that's why what we saw with when we had no non-bonding electrons around the central atom, the electron pair geometry and molecular geometry is because those electrons are now being shared in a bonding situation, they all kind of move together, basically, the non-bonding electrons, the bonding electrons. When we get situations where we have non-bonding electrons involved on the central atom, what that basically means is those non-bonding electrons are sort of, they're not really free, but they're sort of free-ish in the sense that they're only really kind of attached to one atom. And that gives them a little bit more room to kind of move about. And it's really what occurs and why we see a different molecular geometry name when we have these non-bonding electrons there is it gives a little bit more freedom. And it also gives freedom to things that are bonded to also move a little bit more because they're not all fixed together with all these bonds that are happening and all the electrons sort of bonded together. So the molecular geometry is really a combination of how many electron pairs there are around the central atom and how many bonds, which really means, what types of electrons you have there. So again, in this situation here, we have a lot of non-bonding electrons, which allows them to kind of spread themselves out in this triangle sort of situation. And that gives these guys the freedom because also there's not 3 other atoms in the way, right, that also are going to interact with each other. Because those 3 other atoms are not present, it gives those bonding atoms a chance to really kind of spread themselves out from one another. So the overall molecular geometry is sort of a combination of both of those things. Really, how many electron pairs are present, what types of electron pairs, and really how many bonds as to how flexible the overall shape is. And that's why what we're seeing here and what we've been talking about is really the only name that changes is the overall sort of three-dimensional shape of the molecule. And it's because it has that extra ability to sort of move a little bit more than it would if everybody was bonding electrons or bonds. Other questions on that? Okay. So we have that linear. And again, like I was saying, you want to make sure, obviously, that this linear here that we're talking about is our expanded octet and not, again, our two electron pairs and two bonds that are occurring. Another sort of expanded octet that we will come across in terms of sort of geometry here is one where we look at the central atom. And again, if we look at the central atom and count up how many electron pairs, we have 1, 2, 3, 4, and 5 electron pairs. Again, we're now into obviously still the expanded octet here, 5 electron pairs. And again, here we now have 1, 2, and 3 bonds in this case. So with our 5 electron pairs, again, our electron pair geometry name is not going to change. It is still going to be triangular bipyramidal. Now, because we actually now have one extra bond, so you can kind of see the difference from what we were just talking about in this last one. In this last one here, we had also our 5 electron pairs, but we only had 2 bonds. Now, adding that third bond with that third atom that sort of locks those electrons into place, you can see that we now have to take into consideration, you know, how close these bonds or these atoms can get to each other in terms of spacing. And it creates now a different sort of shape because of the presence of those bonds, along with obviously these non-bonding electrons, which are going to try to go obviously away from each other as possible. So as these electrons go away from each other, these guys, which are sort of in that linear arrangement, also now find themselves, I got to kind of keep a distance from this guy and also kind of keep a distance from this guy. And what ends up happening is we end up with a molecular geometry of what is referred to as T-shaped. And you can kind of see the T-shaped in it. If you look at it, it's just kind of how it's drawn. It looks like basically a T, right? So you got kind of like an upside down T, basically. So yeah, or if you want to look this way, you know, it kind of looks like a T on the side, but basically makes this shape this T-shaped. Again, it's going to have a bond angle a little less than our trigonal bipyramidal in this sense, but it'll still have sort of a 90-degree, as you can kind of see bond angle sort of happening here. Another, and by the way, as we talked about before, again, we get these sort of different positions of these atoms, again, sort of along the axis here is axial positioning. And again, you could kind of think about it kind of through the middle there, the equator, if you will, kind of equatorial sort of positioning that's basically happening. So 5 electron pairs, but only 3 bonds gives us a molecular geometry shape of T-shaped. Let's take a look at another one that has 5 electron pairs around it and some of the differences here that we see in this one. So again, if we look at this, we're looking at our central atom. And as I mentioned just a second ago, basically 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs, and 5 electron pairs. So just like before, that is going to give us our same electron pair geometry shape, a triangular bipyramidal. Again, kind of building back in the bonds here, we went from 3 where we got this sort of T-shaped to now we got 4 bonds that are happening in this particular case. Again, the presence of that extra bond brings some different considerations like how close these guys can get to each other, these bonding to bonding guys, also our non-bonding to bonding guys as well. And it actually ends up in this shape, which is referred to as seesaw. This is what is referred to as a seesaw for obvious reasons here. Looks like a seesaw, teeter-totter, whatever you like to call it there. It creates this sort of seesaw with obviously our non-bonding electrons kind of coming in this direction, trying to get away from each other. Again, this is the consequence of adding more guys is they got to kind of keep distances from each other and then also keep distances from our non-bonding electrons that are basically happen as well. Now, in terms of this guy, I believe your book goes with seesaw. Some other books and depending on older ones as well. This is also sometimes referred to as a distorted tetrahedral. It's another name that sometimes pops up around, but I believe our book and most of the newer books and stuff like that, they go with seesaw for the shape of it. But let's see, Shaw. But sometimes distorted tetrahedral will come about, and that's basically this arrangement. But we'll go with seesaw here for ours. So we sort of did some of our triangular bipyramidal expanded octets. Remember that we also got into octahedral sort of geometry, which is our 6 electron pairs. So much like our triangular bipyramidal, these expanded octets also can have some non-bonding electrons involved. So let's take a look at this one and sort of see what we got going on here. When we look at our central atom, it has 1 electron pair, 2 electron pairs, 3, 4, 5, and 6 electron pairs, but only has 4 bonds in this case, right? So 1 bond, 2 bond, 3 bonds, 4 bonds in this particular case. And basically our 6 electron pairs, again, that name does not change. So it is still going to be octahedral in terms of the way the electron pairs are arranged around the central atom. But here again, we got our bonding electrons near bonding, non-bonding near bonding, and non-bonding near non-bonding electrons. And because of the presence of these 4 bonds with the 6 electron pairs, what ends up happening is the molecular geometry of this guy ends up being a shape which is known as square planar. And you can kind of see it right here. The bonding guys make a square within the plane, basically. There you go. So the bonding guys basically make a square within the plane, and it gives you that what is referred to obviously as square planar in this particular case. Again, these guys really do end up being just basically a square in terms of its arrangement. So 6 electron pairs and 4 bonds, octahedral for electron pair geometry, and square planar for our molecular geometry. And the last sort of new one I'm assuming for you guys in terms of geometries is again an expanded octet here in our octahedral. We look at our central atom, we end up with still 6 electron pairs. So again, counting lines, counting dots, doesn't matter. 1, 2, 3, 4, 5, 6 electron pairs, but only 5 bonds. So much like the previous one with our 6 electron pairs, the electron pair geometry is going to be octahedral. And in this case, again, we got all those interactions plus that one sort of that one non-bonding electron. And this obviously has 5 bonds here. It creates this what is referred to as square pyramid. And again, kind of makes a square and this pyramidal type shape kind of coming down. Badly drawn square there on the bottom. And it makes this square pyramid shape for the molecular geometry here. And that would be obviously our expanded octet in this particular case. So these are the geometries that you are responsible for. You do need to know the electron pair geometry. You need to know the molecular geometry. Obviously, if you draw a Lewis structure, you need to be able to do this. What is the best way to do this? Honestly, most people cannot visualize three dimensionals in their head. The best way is to kind of memorize it, kind of make a chart. How many electron pairs, how many bonds. So if you just take the top stuff that I drew on every slide here and put it into a chart with how many electron pairs and bonds around the central atom, that's really the best way to sort of learn these if you're not sure, and kind of put them together. Here's a chart, not from your book, but you have a similar chart again. You can see that typically speaking, when we start introducing those non-bonding electrons, so here, no non-bonding electron, everybody's the same. We start getting everybody the same. We start introducing some dots. We get some differences here in the molecular geometry name. We also start to see that the bond angle gets a little bit less than the all non-bonding bond angle. So here with our tetrahedral, these guys have dots and some different molecular geometry names. And again, some differences there in the bond angle that basically occurs. Same thing here, no non-bonding electrons, both the same name. Start introducing some non-bonding electrons. We start to get some different shapes. And obviously we get some different, a little less in terms of our sort of bond angles that are happening along here. So really kind of the best way to do it is to make a table sort of like this and just go electron groups is a fancy way of saying electron pairs, and bonding groups is a fancy way of saying bonds. And again, personally, that's the way I sort of learn it. Electron pairs, bonds, electron pairs, bonds, and the corresponding names that go with them. So, that's sort of a very good way to sort of kind of put them together and do it. You are responsible for the electron geometry name or electron pair name and the molecular geometry name. So you do need to know both electron pair name and the molecular geometry name. And again, obviously electron geometry is the same thing. Bond angle, you should be familiar with bond angle. I'll be honest with you, I don't know if I'll ask you the bond angle, but you should be familiar with it. Maybe I'll ask it as like an extra credit type question, but I say you should be familiar with it, but definitely you need to know the electron geometry and molecular geometry. So obviously you need to be able to, at this point, be able to draw a correct Lewis structure, be able to calculate things like formal charge, be able to figure out bond polarity as the individual bonds polar or nonpolar, and be able to figure out the electron pair geometry name and the molecular geometry name. Any questions up to this point? All right, so I think we are pretty much done here for this. When is our next quiz? To be honest with you, we probably are going to have a quiz sometime next week, I think, and it probably will be on all this bonding stuff. So these next two chapters here, 3 and 4, probably will be when our next quiz will be. I think probably next week. I think. I have to look at the schedule, to be honest with you. Okay, so we will lay it up there for now.